Now we come to the second part of our first lecture, in which we will learn about the standard state space representation of dynamical systems. The part of the lecture before this was on introduction to the course, and thereafter some elementary definitions of the course. Essentially, the control system engineering is an interdisciplinary subject. The control system engineer has to deal with variety of systems, as we recalled some examples of the systems around us during the course introduction. One may be required to deal with a power system. One may be required to deal with a chemical plant. One may be required to deal with food industry or paper industry. It may be a sugar producing mill. It may be a cloth industry. It may be mechanical or robotic system, or several such type of systems. It may be a biomedical system, biological system. Now, if we expect the control system engineer to know all these subjects, the life of a control system engineer will be very tough. So obviously, the real situation is not that. The subject experts are available around control system engineers, and they are there to help the control system engineer to deal with the systems. However, the control system engineer is required to transform the information available from the experts into a suitable form from which onwards the control studies can proceed. As I have told in the previous part, it could be in the form of a transfer function if one wants to study systems based on the classical approach. However, we are not going to do that. We will very rarely make use of transfer functions. Most of the time, we will make use of state space approach. And the feature of state space approach is that in this, the system or the process under examination is represented by a system of first order differential equations. First, we define what we mean by a system state. The state of a dynamical system is a set of physical quantities, the specification of which at the initial time t0, along with the knowledge of input for time equal to or greater than t0, completely determines the evolution of the system. Please take note, in the second line in this definition, instead of this set of physical quantities, we have said a set of physical quantities. Obviously, the definition implies that the set of physical quantities which can qualify as the state is not unique. There can be numerous choices possible. Other thing to analyze in this definition is the initial time. What should one understand by the initial time t0? Is it the time when the system was started, or is it the time when we started studying the system, or is it something else? Obviously, t0 is generally a time when the system is at a steady state, most of the situations, but that is not necessary. t0 can be any arbitrary time. It can be the present time, or it can be a time in the recent past, or it can be time in long past. It is purely arbitrary time. But the thing is that at t0, we have the knowledge of the set of the physical quantities. And therefrom, t0 from onwards, we have the knowledge of the system input. And these two things, based on these two things, we will be able determine the state of the system subsequent. So as I told already, one must note the specific quantities that define the system state are not unique, but the number of physical quantities which constitute the set, the state, is unique, and this number is called the system order. Let us interpret this definition with the help of two examples. First example is that of a very simple second order ordinary differential equation in which the left hand side is the second derivative of the quantity x and the right hand side is just a constant 2a, and a is not equal to 0 in that. A few very simple mathematical manipulation steps are shown here. The second order differential equation can be solved in these three steps, and the solution will be x equal to at square plus bt plus c. In that, a is given already, you can see. However, b and c, these are to be evaluated from the knowledge of initial condition. And one choice of initial condition could be the knowledge of dx by dt, or the knowledge of the first derivative of x at t equal to t0 or t equal to 0, along with the knowledge of the quantity x at t equal to t0 or t equal to 0 in this case, will be adequate to determine d and c. In fact, d is the first derivative itself at t equal to 0, and c is the x itself at t equal to 0. The knowledge of these two are sufficient to have the solution of x with time, because a is already known. So this dx by dt at t equal to t0 and x at t equal to 0, if these constitute a set, then that set qualifies as the state of this system, which is described by this second order differential equation. Let us next consider a series RLC network, which we often come across in electrical engineering. Applied input is ET, and thus three components, a resistance, an inductance, and a capacitance, are connected in series, and the loop current is IT. And of course, we have also shown in the circuit the charge flowing in the circuit by the symbol QT. Now, if one attempts writing the equation governing this circuit, then by using the Kirchhoff's voltage law, one obtains this equation: ET equal to RIT plus LdI by dt plus 1 by C integral of IT dt. Some of the terms in this are derivative, some other term is integral, and one term is simple R times IT. What we do is we make use of charge instead of the current, and this equation can be converted into what is shown here. ET is L d2q by dt square plus R dq by dt plus 1 by C q into dt. Now, you can see that the knowledge of dq by dt at t equal to t0 and qt, that means electric charge and the rate of change of electric charge at t equal to 0, if these two are known in the circuit, then one will be able to solve for the values of qt or it with time. So in the case of this series RLC network, the two quantities we should know to be able to solve, given Et for time t greater than t0, is the charge stored in the capacitor at initial time and the current flowing in the circuit at initial time. In other words, the charge and the rate of change of charge at t equal to t0. If these two are known, then we can get the time variation of current or charge in this circuit as time progresses beyond t equal to or t greater than. Well, these two examples are just to demonstrate that how we could choose the set of quantities which may constitute the system state, although the two quantities are not unique. Now, with this background, let us come to the standard state space representation of dynamical systems which have been introduced in 60s. The standard state space representation consists of n first order differential equations given as this. I read a few of them. X1 dot t equal to f1, x1, x2 and so on up to xn, u1, u2 and so on up to un and time. Similarly, x2 dot is f2 of x1, x2 etc. up to xn, u1, u2 so on up to un and time. And likewise the other state variable derivatives. And finally, xn dot equal to fn, x1, x2 and so on up to xn, u1, u2, u3 etc. up to un and the time t. Look carefully at these equations. On the left hand side, we have the derivatives of quantities x1, the first derivative with respect to time, x1 dot. And on the right hand side, we have expressed them by various functions f1, f2, etc. However, each function has the same arguments. The set of x1, x2 and so on up to xn, u1, u2 etc. up to um and time t. This is the standard representation. I repeat that in this, on the left hand side we have the time derivatives of the quantities x1, x2 etc. and on the right hand side we have functions in which the arguments are these quantities x1, x2 etc. and the inputs, and in addition to them the time. These quantities x1, x2 etc. these represent the state variables. The quantities u1, u2 etc. these represent the inputs, and t, as we understand, represents the time. The beauty of the standard state space representation is that it is capable of handling more than one input, or in other words, multiple input systems. These equations can be represented in concise form in the vector form as x dot equal f of x, u and t, where capital X is a column vector consisting of all states x1 to xn. Capital U is also a column vector of all the m input variables u1, u2 etc. and t denotes the time. Note that f is containing m plus n plus one argument, the number of inputs plus number of states, and in addition the time, total n plus one arguments. And as was told earlier, capital X, which contains the state variables, is called the state vector, and capital U, that contains the input quantities, is called the input vector. When time t doesn't explicitly appear in the state equation, the state equation takes the form x dot equal to f, x and u. There are only n plus m arguments. Time is not there in this implementation. Then the system is called to be time invariant. This is generally the situation. Most of the time we come across time invariant system. However, there are a few situations we come across systems which are time varying, and in that case the representation which was given in the previous slide was good. If the system is linear, then the representation of the system changes in this form. X dot equal to ax plus bu. The system representation becomes in such a way, please note, that the time derivative of the state vector or the time derivative of each state is a linear combination of the states through A and linear combination of inputs through B, or together the derivative of each of the states is linear combination of the states and the inputs. So in case of linear systems, it becomes a linear combination, and in this case A, which is called as system matrix, is a square matrix n by n, and the B, which is called as input matrix, is an n by m matrix. And as the system is time varying, in explicit manner if they are represented, either sum or all the elements of matrices A and B will be varying with time. For example, it is written as A11T, A12T, etc., A21T, A22T, etc. Generally, the physical systems are nonlinear. If the system encountered is a nonlinear system, it can be linearized around the point of equilibrium or any other operating point and represented in form of the linear systems, which was given in the previous slide. X dot equal to ax plus b. Come across situations in which besides being linear, rarely the elements of the system matrices and the input matrix, they depend on time. Or in other words, A and B are constant. In that case, the representation obtained is called as linear time invariant or LTI system representation. You can see that we have dropped the t which was coming along with A and B. So instead of AT and BT, we have only A and B, notifying that A and B are constant matrices. Along with states and input, one is actually interested in the output also. So in the standard state space representation, the output y is a state vector containing as column, the output y is the output vector containing as column all the outputs y1, y2, etc. We have assumed p outputs, so we have the last element as yp, and this is a p column vector or a column vector of length p, and it is expressed in case of linear time varying system as ct times xt plus dt times vt. That is, the outputs are linear combination of states and inputs both. However, in most of the situations, the outputs are only the linear combination of states. and they don't directly contain the input term. So yt will be generally represented as ct times xt, and in case of linear time invariant systems, it will become y equal to cxt. We summarize the chapter. The standard state space representation of a dynamical system consists of a set of n first order differential equations, where n is the system order. The first derivative of each state is expressed as a function of the states, inputs and time. When the system is linear, the first derivative of each state is expressed as a linear combination of states and inputs and time. If besides being linear, the system is also time invariant, then the combining coefficients are constant. The outputs of the system are expressed as functions of states, inputs and time. In case of linear time invariant systems, the outputs are expressed as linear combination of states and inputs only. The combining coefficients are constant. There is some exercise for you. You can consider the second order ordinary differential equation which I have shown to you in one of the early slides. d2x by dt square equal to 2a, where a is a constant. Suggest some initial conditions different than what I had shown to you, based on which one can determine x state and which can qualify as the system state. Test whether or not the following ordinary differential equations linear. dx by dt equal to 2x plus 5. We have to determine whether this equation is linear or not. The second one given to you is, there the variable is not x, it is y. dy by dt is e power t. So you have to determine whether this equation is linear equation or a non-linear equation. And for both these equations, you have to find out, is any of these time invariant? Which of these is time varying? And you have to give reason supporting your answer. We come to the end of part 2 of lecture 1 here, and see you again in the lecture 2. Till then, goodbye.